Hello, let's begin section 3.3, which is about optimization. Let's start with the absolute maximum value and absolute min. We've talked about local maxes and local mins. The absolute max of a value of function is the largest value of the function on its domain. The absolute minimum is the smallest value. So when we say smallest value, means smallest y value of the function on its domain. Okay, so if you look at these graphs here, right, this one has an absolute min and an absolute max. Okay, for example, this point here, that's the absolute min, absolute max. This point here we would consider a local min, but it's not the absolute min. This is a local min. Okay. The absolute min is the smallest value in the domain of this function. Same thing here. The absolute max is the largest value in the domain. And this one has neither a min nor a max, because when you see a graph like this, you assume there are arrows here and it's going to go on forever. So there's never going to be a max or a min. Okay. Let's look at optimizing functions. So if you have a continuous function on a closed interval, the continuous function has both an absolute max and an absolute min. Okay, so think about any kind of function. Let's even look at this function that we have here. Okay, there's no absolute max or absolute min, right, on the domain of the function. But if I look at a closed interval, so I'm only looking at the function from here to here, let's say, then I can find an absolute min, okay, which would be probably this one, and an absolute max. Okay, so you have to find the critical numbers, which is where the derivative is equal to 0 or undefined, right? So here's the possible critical number right here, this x value, and you have to evaluate the function at the critical numbers and at the endpoints. Like for this function, the max occurs at the endpoint, right? So that's what you want to do, is evaluate at the critical numbers and the endpoints, and then the largest and smallest values will be the absolute max and min. Let's do an example. So it says optimize this function on the interval 0, 3. Find the absolute extrema. So when it says absolute extrema means max and min. So we want to optimize, so we need to find the critical numbers. In order to find the critical numbers, we have to take the derivative. Okay, so that's 3x squared minus 18x plus 15. Okay, and we have to ask ourselves, where is this undefined? Well, it's not. It's defined everywhere. It's a polynomial, so there's not going to be a critical number due to its being the derivative being undefined. So then we have to say, okay, set the derivative equal to 0. Okay, so we set the derivative equal to 0. I'm going to factor out a 3, x squared minus 6x plus 5 equals 0, and then I'm going to divide both sides by 3. So once I divide both sides by 3, this is gone. And then I can factor this as x. So I want to think factors of 5 added to give me negative 6, right? So negative 3 and negative 2. So that's x minus 3 and x minus, oops, that's not right. That's factors of 6 that give me 5. I want factors of 5 that give me 6, so that's 5 and 1. 5 and 1. Okay, and both of these have to be negative. X minus 5, x minus 1, set that equal to 0, and then we get x equals 5, 1. Okay, these are my critical numbers. Now it says evaluate the, so we did step 1, find all critical numbers. Now it says evaluate f at the critical numbers and at the endpoints. So I need to evaluate, let me look at the endpoints, f of 0, f of 3, and then the critical numbers are 1, and look at 5. 5 is not inside this interval, is it? So we are going to ignore this. Oops, let me do this. Let me change my pen color here. So we are going to cross this one off because it is not in the interval 0, 3. Okay, so we don't want to look at that one. So we only want to evaluate at these 3 values. Okay. So what are we doing? We're plugging this into the original function. So let me pull up my calculator here. Okay. And let's do y equals x cubed minus 9x squared x cubed minus 9x squared plus 15x. Okay, and I want to do second table, and I want to evaluate it at 0, 3, and 1. Okay, so these values are in there. Are these? You just check these. Yeah, these are asked. So if I change this to 2, yeah, so that changes that, so it's 1. Okay, so when x is 0, y is 0, 0, negative 9, and 7. So what is the largest value? 7 is the largest value, right? The largest y value. What's the smallest y value? Is this one, negative 9. Okay, so our max we have a max at 1, 7 and min, okay, and this is absolute max, absolute min at 3, negative 9. Okay. And we can always graph this and check. So let's do that. I already have this in y equals. Okay, let me change my window. Let me change my window to look at from 0 to 3. And my y min should go from, let's say, negative 10 to 5. We'll go by ones. Okay. So that is what that function looks like. So you can see that the max occurs at, oh, I didn't go high enough, window. I have to go up to y max. Let's make the y max go 10 also. Okay. So you can see, oh, where's my max occurring? At 1. Right? Where's the min occurring? So the max is occurring at the critical point, at the critical number 1. The min is occurring at the end point at 3. Okay. So obviously you can check with your calculator, but on the quiz and test I want to see this work, okay, this calculus work. Recall the second derivative test. That's when you take the critical numbers and you plug them into the second derivative, and if it's positive, then you know it's concave up, you have a min. If it's negative, concave down, you have a max. Okay. If a continuous function has only one critical number, then the second derivative test can be used to find the absolute extrema. Let's look at this example. So here's the value of a timber forest is given by this function, thousands of dollars, where t is greater than 0, right? T is time. Find when its value is maximized. Okay, to maximize a function, take the derivative, and this is 96t to the 1/2 minus 6t. Okay, so I'm going to pull the 1/2 outside. 1/2 times 96 gives me 48. Remember we do this business? So t to the negative 1/2 minus 6. that is the derivative. This becomes 48 over, whoops, 48 over square root of t minus 6, okay, and I want to set this equal to 0, okay. When we set it equal to 0, let me add 6 to both sides, multiply by root t, so we get 48 equals 6 root t, okay, and then we divide by 6, so we get 48 over 6, which is 8, is equal to square root of t, and then we square both sides, so we get 64. Okay. So t equals 64. So that's where the derivative is equal to 0. Okay, and I'm going to put a little note here. Note. V prime t is undefined when t equals 0. So the derivative is undefined when we have 0 in the denominator here, right? Square root of 0 is 0. But notice that t equals 0 is not a critical number because it is not in the domain. Notice how our t is strictly greater than 0, right? So t equals 0 is not even in our domain, so we're not going to consider that a critical number. So t equals 64 is the only critical number. Okay. So now it says find when its value is maximized. Okay, use the second derivative test. So what we're going to do is take the second derivative. So here's my first derivative. Let me take the second derivative, v double prime t. Again, you pull the negative 1/2 on the outside, so you get negative 24 t to the minus 1/2 minus 1 is minus 3/2. Derivative of negative 6 is 0, so this becomes, right here, negative 24 over square root of t cubed. Okay. Now I want to take the critical number and plug that into the second derivative. That's what the second derivative test tells me. Okay. So that is v double prime of 64, which is negative 24 over square root of 64 cubed. Square root of 64 is 8. 8 cubed is 512. And this is negative, right? This is negative. So negative, when your second derivative is negative, that means it's concave, the function is concave down, which means we have a max. Okay, so indeed the value is maximized, or the value of the timber forest is maximized when t equals 64, so in 64 years. Value maximized. Okay. This is also the same procedure to finding the minimum, right? So basically, you could ask the question, what's the whole point of doing this? When you take the derivative and set it equal to 0, that procedure is used to find the max and the min. How do you know you're actually getting the max and not the min? That's where the second derivative test comes up. Because this is negative, it's concave down, we know we have a max. If our second derivative was positive, then our graph would be concave up and we would have a min. Okay, luckily we do have a max here, which is good. So the value of our forest is increasing and not decreasing. Okay, let's look at maximizing profit. Okay, so profit is revenue minus cost. Revenue is the money that comes in, cost is the money that goes out. Well, how do you find revenue? Revenue is the price times the quantity, right? How many items are you selling and at what price are you selling them at? So when you take this and plug it into this function, you get profit equals price times quantity minus cost. Okay, P of X is usually the price function. It's usually given. Let's look at an example in your book. Okay, and then after we do the example, I also want to look at page, we'll also look at number 36. Okay, so the example in your book is here, okay, on page 211, example 3. It cost the American Automobile Company $8,000 to produce each automobile, and fixed costs, rent, and other expenses that do not depend on the amount of production are $20,000 a week. The company's price function is given by P of X, where P is the price at which exactly X cars will be sold. How many cars should be produced, for what price, and what's the max profit? So I've written this out here. Let's go ahead and find X. So that's what the first question says, is how many cars should be produced. Okay, and the way we want to find that is we want to maximize the profit. Okay, so first thing we have to do is find the profit function. Profit is, we know it's price times quantity, that's the revenue, minus the cost. Okay, so the price they give us as 22,000 minus 70x. Okay, and the quantity is X. So this is the price, and that's the quantity. Okay, minus the cost. So I need to find the cost here. So let's write down our cost function first. So it costs $8,000 to produce a car, and the fixed cost is $20,000, right? So if you're not sure, you can make yourself a little table, okay? And cost. So if I produce 0 cars, what's my cost going to be? Well, I'm not producing anything, I just have the fixed cost, rent and overhead, right? If I produce 1 car, that's going to be $8,000 for that car, plus the $20,000 fixed, which will be $28,000. Oops, too many zeros. If I produce 2 cars, it'll be 2 times 8,000, which is 16,000, plus the $20,000 fixed, right? And let me rewrite this one. Oops. Okay, let me solve it. So the first one was, it was $8,000 plus 20,000 fixed. The second was $16,000 plus 20,000 fixed. The third was, it's going to be 24,000 plus $20,000 fixed. So for X, any number of cars, it's going to be $8,000 for that car, for each car, plus $20,000 fixed. Let's see what's going on here. Okay, plus $20,000 fixed. So that is the cost function, $8,000, 8,000x plus 20,000. Okay, so this part goes here. Okay, so minus, and don't forget your parentheses, you're subtracting this whole function, this whole thing. Okay, so now we have to simplify this. So I'm going to multiply the x here, so I get 22,000x minus 70x squared minus 8,000x minus $20,000. Okay, so then I'm going to subtract 22,000 minus the 8,000. So what does that give me? So let me write it using the proper notation. So let's put the x squared first, and then 22,000 minus 8 is going to be 14,000. Okay, and then minus 20,000. Okay, and that is our profit function. Profit function is usually written as capital P of x. Okay. Now I want to maximize the profit, right? So we want to maximize the profit. So we take the derivative and set it equal to 0. So bring the 2 out front, we get minus 140x plus, whoops, 14,000. That's the derivative, and we want to set this equal to 0. Okay. So when we set this equal to 0, subtract 14,000, divide by negative 140, and we get x equals 100. Okay. This is my critical number. And this is part A, what we've solved for, find x. Okay. Now, it's always a good idea to check to make sure that you're maximizing and not minimizing. So, let me do this in red pen. Check max, not min. So let's take the second derivative. The second derivative would be negative 140, right? That's the derivative of the first derivative, and that is negative, less than 0, so we know the graph or the original function is concave down, and indeed when it's concave down I do have a max. Okay. So we found x equals 100. Now they say find the price. Find p of x at the critical number. That's what that is asking. Okay, let's go back. It says, for what price should they be sold? Right? So let's plug x equals 100 into the price function. 22,000 minus 70x. That's the price function. Okay. So that's going to be lowercase p of 100, which is 22,000 minus 70x. That's going to be 3, 0, so 7,000, which is what? 15,000. Okay. So the price of the car should be $15,000 per car. Okay. Okay, letter C asks what is the maximum profit. So we're going to take what we found for x, which is 100, and plug it into the profit function. So we want to find capital P of 100. Okay, so that's negative 70 times 100 squared plus 14,000 times 100 minus 20,000. Okay. So that's minus 70, 100 squared, so that 100 has 2 zeros, so you square it, you get 4 zeros plus 14, and then 1, 2, 3, 4, 5 zeros minus 20,000. So then this gives you minus 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 zeros plus 14, or this is 1.4 million. Whoops. Minus 20,000. So 1.4 million minus 700,000 is 700,000 minus 20,000 is 680,000. Okay, so that is the max profit. So basically your book does the same thing, and you can go through and read the example if you so desire. Okay. Let's look at number 36, I think it was. Yeah, 36. So 36 says, City Cycles Incorporated finds that it costs $70 to manufacture each bicycle and fixed cost $100 per day. This is the price function. Find the quantity City Cycle should produce and the price it should charge to maximize profit. Okay, so what I want you to do is take a minute, work out this example, pause the video, work out this example, and then just try it on your own, and then I will work it out and show you, and you can see if your work matches my work. Okay? Alright, so it costs $70 to manufacture each bicycle. Fixed cost or price function is given. So find the quantity City Cycle should produce and the max profit. So we want to find the profit function, right? So profit is capital P of X is the price times the quantity, that's times the quantity Q of X minus the cost function C of X. Okay, price function is 270 minus 10x. The quantity is X, right? That's how many bikes should be produced. And the cost, it costs $70 to produce each bike, and fixed costs are $100 per day. Okay, so let's again do the same thing we did before. 270x minus 10x squared minus 70x minus 100. Okay, and then we get minus 10x squared. 270 minus 70 is 200x minus 100. And then we can factor out, well, we don't have to yet. That is my profit function. Let's find the derivative. Right, we want to maximize profit. So take the derivative, minus 20x plus 200. Okay, set that equal to 0. Subtract 200. And we get x equals 10. That is honestly a coincidence. I did not expect that to happen. Okay, so you're always, we got 10 for the last problem too, and that's just unusual. Okay, so that's how many bikes should be sold. So find the quantity City Cycle should produce, and then don't forget to take the second derivative to check. When you take the second derivative, you get minus 20. That is indeed a max. Okay. Find the quantity City Cycle should produce and the price it should charge to maximize profit. So the price should be P of 10. So P of 10, which is 270 minus 10 times 10, which gives us 270 minus 100, which is 170. So it should charge $170 per bike. That's the price. Here's what it should sell. It should sell or produce. What is it? Manufacture. It should manufacture 10 bikes, sell them at $170 a bike, and then the max profit capital P of 10 is going to be minus 10 squared plus 200 times 10 minus 100. So 10 squared is 100 times 10 is 1,000, so that's minus 1,000 plus 2,000 minus 100 gives me 1,000, so minus 100 will be 900. So it'll be $900. Okay. So let's go ahead and check this, right? What you can do is, so again, on your calculator you can check. Okay, I want to see the work, and I want to make sure, and I will check for your work. Okay, if you have the answer, that doesn't mean anything to me. I need to see the work. So y equals, so let's go ahead and do this. 270 minus 10x times x minus 70 x plus 100. Okay, and then we are going to do, let's do zoom standard and see what happens. Zoom 6. X is 10, and this should be 900, so I have a feeling it might not fit on here. Probably won't. Yeah, so my window should go from 0 to, let's say, 15. And my Y min should go from 0 to 1,000. That's the profit. And then the profit function, let's go by hundreds. Okay? And let's graph this guy. Okay? And my max should occur when X is 10. Trace 10. There we go. So the max of 900. So you can check your work. That's the good thing with technology. Okay? So that is it for this section. We will do more applications of optimization next time. If you have any questions, please feel free to get in touch with me. I am available to answer your questions in person, online, over the phone. Okay? All right. Thank you for watching.